Thanks so much for turning up. And thanks for your interest in digital twin. Let me start off with a quick questionnaire. Can I have a show of hands of anybody here who is passingly familiar with digital twins? Oh, we got a few. That's awesome. All right. So I hope this doesn't bore you, but for the folks who are not familiar, let me dive into the technology. Just by way of introduction, that picture there in the slide, that is actually a digital twin. Although it looks photorealistic, it looks like an aerial photograph. It is not. Each one of those buildings, trees, cars, all of those features up there, including the roads, are all part of a digital twin. So they're not only present in a visual sense, but they're all connected together as well. And there are other layers underneath that, so all the utilities are beneath that layer, and the connectivity of the utilities is all preserved. Just so you know. What is the digital twin? I'm not going to read this out, but the fundamental principle of a digital twin is that it is a representation of multiple parts of a system. So it can be physical presence, it can be social presence, it can be virtual presence. All of those pieces are mocked up inside the model that is the digital twin. It uses real-time data. It has computational agents that are resident within the digital twin that allow it to compute from the data sets that are in the digital twin. It includes reasoning, ontology, and we're at TMLS, so it has to have machine learning in it as well. I also won't read this, but I do need to tell you a little bit of a story of where this comes from. So the notion of digital twins has been around for a long time, but it really came into prominence in 2010 when NASA started testing spacecraft with digital twins. So it's generally a bad idea to take a $3 billion spacecraft and destruction test it. That's frowned on. So what instead they did was they instrumented the spacecraft and created a virtual copy of it. And so they could perturb the virtual copy to see how the physical spacecraft would respond, right? Stresses from takeoff, stresses from insertion into orbit, all those things. So NASA made them famous. We had a situation in Christchurch in South Island, New Zealand. You may remember there were some massive earthquakes there. Those earthquakes caused enormous damage in Christchurch. And one of the research council, I run a research council in Australia, and that research council was asked for help to see what we could do about the catastrophe in Christchurch. And I suggested, well, let's explore this digital twin mechanism. So we actually built a digital twin of the desired state of Christchurch after recovery from the earthquake. And that gave us all kinds of insights about people traffic, car traffic, facilities that were going to be needed, where the facilities were needed. It was a wonderful opportunity to replan a city that was fundamentally devastated. So that's a little bit of the background. One more piece to that. There is a digital twin in Singapore. You can look it up on the internet. It's a very well done digital twin of the entire space of Singapore. They picked up on what was going on in Christchurch and picked up the idea. And now if you look around the world, there's a digital twin of Helsinki, there's one in Amsterdam, there's pretty much many of the big cities. And I was just telling somebody, the state of Australia that I come from, Queensland, if you contribute open source data of any form, by definition, it goes into a digital twin. So all the open source data that you can get at for Queensland is part of a digital twin, which enables all of the analytics that you'll see in just a little while. If you leave this little session with three things, just remember these three things. These are the three things that we can do with a digital twin. We can simulate the effects of events and trends, and that includes people, physical objects, and systems. We can explore alternative solutions to complex problems, and those complex problems can be beyond human comprehension, and I'll explain that in just a little while. And finally, abide by obligations to various stakeholders. And the example that we put together for this is the United Nations has a set of sustainability goals. You can read it on their website. You can actually take those sustainability goals and break them down into individual goals for countries. You can break them down further from that to individual companies like RBC, for example, and make them deliverable items inside a digital twin. And by doing that, you can then roll it back up and show measurable change to the sustainability goals, measurable improvement along the sustainability goals. This is a bit extensive. I won't go through the whole thing, but you can certainly have a look at it in the slides later on. So there's a bunch of things that we can do here with a digital twin. One of my favorites is related specifically to RBC, but the question that I use as an illustration is, if RBC changed the 5-year fixed mortgage rate, what effect would that have on climate change? That's a question we should be able to answer. In fact, a whole bunch of those questions we should be able to answer. We can't answer it right now, but I can say that you're probably thinking about, what's the chain? How do we get to climate change from changing a mortgage rate? Well, think about some of the things that might be present in a digital twin that will carry that link. For example, changing the mortgage rate might change the inclination of somebody to buy an EV, an electric vehicle. And if they change their inclination to buy an electric vehicle, the emissions that they're producing will be continued. So we're not reducing emissions there. They might change their mind about upgrading to a larger house. Larger house would usually mean that the insulation is probably more modern, and so the insulation is superior, and therefore they're using less gas to heat the place. So there's a bunch like that. Somewhat orthogonal to that, suppose there was, well, we've just encountered the wildfires. We should be able to simulate those wildfires. It's an incredibly complex model, but we should be able to say wildfires are appearing in these places, the progression of those wildfires through space and time. We should be able to simulate that and see what the effects would be. In fact, the ideal scenario would be to get the firefighters out in front of where you think the fire is going to be, which is a vastly superior scenario to what we have right now, where they're fighting it in place. In the financial space, you might be asking yourself the question, why is RBC bothering with digital twins here? Well, because one of our things is looking after the finances of the country, and flow of funds is a fascinating problem, right? So how are funds moving around the country? For RBC, that's an understanding that would be very valuable, and it's something that a digital twin will do a lovely job of. There's a few others here that I should highlight. Maybe greenhouse gas sequestration per field. You'll see in just a little bit, I have a slide about that. But you should be able to, with a digital twin, if you have all of the parameters in place and all the connections in place, you should be able to say, this farmer's field in 1 year is sequestering this much greenhouse gas. And that's a powerful thing to be able to say. I'll draw your attention to one of the thought articles in rbc.com that was written recently, where there's an assertion there that farmers who are sequestering carbon, by definition, by growing crops, should be compensated for it. Seems like a really good idea. The illustration here is to show that there are multiple layers to this. So there is, of course, the physical layer. So everything in a digital twin, in most cases, relates to a physical entity. Not necessarily always. In the case of a process digital twin, for example, you may not have location information present. But in general, it's reasonable to say there's location information present. You've also got the virtual connections, right? So connections between me and somebody else. I've paid that person some money and some goods have changed hands. That relationship can appear in a digital twin. So that's a virtual layer, but also the social layer. So I may know that person, and the social connections are mineable as well. Now, of course, some of this gets a bit intrusive, and there's a whole swath of conversation that you can have about invasion of privacy, and well, I'm going to set that aside for now. We'll come back to that. This is the money slide. This is the one that explains what all the pieces are. So fundamental underneath the digital twin is usually a knowledge graph. And if you're not all that familiar with knowledge graphs, think of a place where you can store and construct axioms. So this is related to this, and this is related to this, therefore these pieces are related together. It's a lot more complicated than that, but the fundamental idea is that you can build up an understanding of an entity. You can build it up by pieces. So this is where it suddenly becomes interesting to put a very complex model together, right? So you can now say, I assert these things. So these rules are going into my system, and I'm going to assert these. And then I find some more information over here, and I say, okay, I'm going to assert those in as well. Provided I am disciplined in the way that I add this data, I can actually build up a complex model, piece by piece, of something that I cannot possibly understand myself or explain. But you notice that I said there's some rigor there as well. And that's really, really important, and we'll come back to that later when we talk about ontology. Machine learning is present, so a digital twin, by its nature, encompasses active agents. And some of those active agents can be predictive engines. So we have a machine learning model that calculates property value very accurately. Property value depends on a set of features. If some of those features are perturbed within the digital twin, that model kicks into action and recalculates the property value based on those features, and that's resident in the digital twin. One of the biggest problems that we've faced in the past was entity resolution. How do I know that John Smith over here is the same as Jack Smith over here? A digital twin can help you with that as well, not because it resolves that direct connection, but you can have an inference path that relates to other information about those two entities that gives you reason to suspect that they're the same person. Federation I will skip over for now. Ontology I'll come back to. I talked about embedded models. Active feedback. So not only is a digital twin react to individual stimulating it, but if it's connected to external data sources that move, change, then it will respond to those as well. So it's effectively a live, connected model of the outside world. Location intelligence, of course, is there. The spatial information is there. That's essential. Real time, I'll come back to. We refer to the process of perturbing a change through the digital twin as ripples. Don't know if that term will stick, but the idea is that if I perturb something here, I can see the effect of that move its way through the digital twin. Visualization, you saw a little bit of visualization there. We also bring in data from imagery. So we do feature extraction on imagery. That feature extraction mechanism generates data which feeds into the engine as well, and that can be live as well. So the digital twin that we built at RBC is tethered to the Sentinel hub, which sees directly to the data that comes back from the Sentinel satellites. So we can respond to that instantly. Geodemographics and hybrid AI, which I will come back to. Now, I said there was a knowledge graph. Let's talk a little bit about ontology. So the ontology aspect of this fits in two places. Not only does the ontology offer a rigid mechanism for controlling the structure of the data, the schema of the data, and prevents you from introducing things that don't relate well. For example, in our digital twin, you can't marry your sister. It just says you can't do that. So that would be a violation of a lot of things, but it's a violation of the digital twin rules. And there's reasoning involved as well. So the ontology structure allows you to do reasoning, and that reasoning can come up with inferences that you might not otherwise find. And I'll talk a little bit more about that in a moment. This is, okay, all disclaimers here. I drew this diagram. This is a pictorial representation of the ontology that we built. This is vastly simplified from the actual ontology. But this ontology is related, you can see, is related to agriculture. So how are we relating this to agriculture? Why does RBC care? Well, the second largest sector for RBC in this space is agriculture. And one of our big mantras here is how can we help farmers be more successful, feed the world, but also how can we help them reduce their emissions? How can we help them reduce the effect on the climate? On the left-hand side, you can see here how those relationships build up. So this ontology structure gives you the relationships that are permitted so that when I put data into the digital twin, that data inhabits these rules, and these rules control how the data is put together. So there's a little example here. So farm is spatially defined by a farm boundary, and the farm boundary has a legal description. But a farm also has a legal description, so you can see that connection there as well. Which now you can infer and say, okay, the farm has a legal description, and I've got a description of the farm boundary. Those two, I can now infer a connection between those. Very simple example. This is a bit more detailed. I didn't draw this one. This shows you the structure that we put together with the ontologies. Now, the thing about ontologies is you don't have to define the whole thing yourself. There's lots of them out there. And in our particular case, we found 8 strong ontologies that fit the use case that we were interested in. We extracted the pieces that we needed, or we referenced the pieces that we needed, and that constructed an ontology for us, including our own ontology subject matter, that has 15,000 axioms in it. So those are the rules by which this digital twin is controlled. There's real-time data. This is actually real-time data. These are sensors that are in the Fraser River. Those sensors actually exist. They're IoT sensors. And if you look up digital twin, for example, on the Microsoft site, they very much emphasize their digital twin as being an IoT connection. That doesn't necessarily follow that that's always the case, but that's how Microsoft think of them. And finally, I'm not sure if folks know what neural symbolic AI is, but this is a mechanism where you're actually building AI, you're actually building a machine learning engine, but you're building it subject to the constraints of an ontology. So it basically says, the way I've always explained it is the human brain is the model for AI, right? Everybody knows that. But the human brain is capable of chaotic thought, and if you've heard any of the presentations this morning, AIs are capable of chaotic thought as well. What neural symbolic AI or hybrid AI does for us is it puts controls in place that keep that logic, keep that AI thinking straight, which is which is a very powerful thing. And the way, so the human brain thinks in AI, the human brain thinking about mathematics is now constrained by the rules of mathematics. So that sort of parallels the idea of an ontology controlling a neural symbolic. A couple of pictures here to show you some of the data that we've extracted in the digital twin that we built. We use various mechanisms here to isolate the edges of the properties to understand where houses were, boundaries of houses, looking for changes, right? So some of the RBC teams are very interested to see how communities change over a period of time. And now we get the pretty slide. So it's quite a bit to show on this slide. This is illustrating the location intelligence stuff that belongs to the digital twin. So top left-hand, I don't have a pointer, but top left-hand corner here, what that is a real-time feed from the Sentinel satellite that gives us soil moisture. And the way it does it is picks up static radiometry of the soil, and in this particular case, we've color-coded it. Now, if you look in the top right-hand corner of that picture, the picture on the left there, you can see blue circles. And those blue circles are actually irrigation booms. So the way the irrigation works is it's pivoted in the center, and there's a big, long boom, and it swings around and it waters that whole area. Obviously, because it's circular, it leaves the corners out. And so you can see the corners are actually drier. What's interesting, though, is the third circle down you can show is actually showing as dry. And we talked to that farmer, and he was surprised to see that that field was showing as dry and went away to try and figure out why. But we already had this in the digital twin. Further down from that, you'll see like 1, 2, 3, 5, 6 down on the right-hand side of that picture is another circle, but you can see there's a circle in the center of it that is showing as dry or drier. In actual fact, what we identified there was that the nozzles on the irrigation boom towards the center of the field were clogged, and so there was hardly any water coming out of them. So the interesting thing is that the farmer wouldn't know that, because these fields are 40 acres. So unless he actually drove into the center of the field, he wouldn't know that he's not irrigating that. So you feed that into the digital twin, and that's another piece of evidence that's useful to the projection. Top middle is actually, this is very, very detailed vegetation data. It shows you trees, it shows you shrubs, it shows you conifers, deciduous, it shows you the height of the tree, it shows you crops, it shows you irrigated crops. All of that data combined with the soil type allows us to understand in quite some detail just exactly how much carbon is being sequestered in each area. On the right-hand side, that's a map of soil types. This is government data, so very good government data. And down below, I won't go into that, but that's the NDVI, so that's the index for the actual vegetation. The competency questions that our digital twin was designed to answer. Now, I should say that a competency question is a question you set up to make sure that the path right through the engine actually is working. That competency question, the competency questions we came up with was, when should irrigation commence? When should irrigation be discontinued? And completely orthogonal to that question, who's likely to take over the farm once the farmer retires? So our commercial account managers want to know the answer to all those three. They're all good questions. And if you think about it, the model behind this to understand when irrigation should commence is insanely complicated, because you've got soil types, you've got soil permeability, you've got soil types at depth, you've got rainfall, you've got, if it's spring, you've got snow melt, you've got the topography to take into account. It's an insanely complicated thing, and actually we haven't yet found anybody who's made a model that works. So this is a beautiful example for a digital twin using machine learning. I don't need to go through this. We're at 4 minutes here, so I'll just skim through this a bit. I already mentioned that we generated 15,000 axioms from 8 published ontologies plus our own ontology. We built in a reasoner. One of my favorite pieces of the digital twin here is that we actually built in a prologue. And does anybody remember prologue? So we built a prologue engine into this, and the prologue engine uses logical reasoning to create inferences and populates those inferences back into the digital twin, which raises a very interesting problem because you don't want to change the golden data that's in the digital twin with the simulation data, but that's another subject. That'll be TMLS next year. And that finishes the presentation for now. Thanks very much for your attention, and I think we actually may have some time for some questions.
It's amazing. There are mic runners going around, so if you have any questions, just raise your hand and they'll come around.
Hi, thank you. First of all, I would like to say in an LLM-dominated conference, it's really great to see some geospatial intelligence applications, right, coming from a similar field, but in the maritime sector. Given your experience with digital twins, I really want to leverage. I guess I'll talk to you after this question as well. What are your thoughts on errors propagating through a digital twin? You know, your precipitation forecasts are a bit off. Your soil moisture might be a little off due to Sentinel-2 resolution, and all of those errors propagate through the final result that you're looking that's coming out of the digital twin. Any advice on what would you do in a situation like that?
It's a very good question. So 2 points here. The first one is that the results of the digital twin are subject to verification, right? So you can test the cycle. So that certainly helps with things that have diverged. But it also lets you correct the ontology. If you've actually built an ontology that's controlling the direction of the digital twin, and it's not quite right, you can see that if you've got a way of verifying the results. In our case, for example, we would probably verify the results by using a different satellite, by using ground truth data, sending IoT devices into the field to do measurements. As long as we've got multiple results there, that gives us a circularity to it. Inevitably, some of the data is going to be doubtful. In fact, I don't want to throw the government under the bus here, but their data on crop types is disastrously bad. Their yield numbers are fairly poor as well. So those are things that we know already, and we can take account of those. But yeah, basically, I think it's testing the end result is the best place to go. I think there was a few questions here.
Yeah, thanks for, it's very refreshing to have a non-LLM talk here. What's your North Star for these types of models 5 years from now? What are the key roadblocks towards achieving that?
Oh, that's a doozy of a question. Ultimately, yeah. So the question really was, what's the North Star? Where are we trying to get to in 5 years' time? Most definitely, this was a first sort of tentative step into the cold water to iron out some of the technology bumps, and that we succeeded in doing. But the next steps would be, let's populate the hell out of this so that we can ask some of those other competency questions that you might have seen in the slides earlier on. That's definitely one. We want to get to the stage where this engine completely understands what's going on with respect to the outside world. For me, the big thing is what can we do about carbon sequestration? How can we mitigate climate change? And that's something that RBC is very passionate about, and I'm particularly passionate about. Yeah.
I have two questions. First, why choosing Prolog over a much more capable proof assistant in math?
Ouch. Ouch.
And
He's
second,
being rude about Prolog. I need help.
second, what percentage of the Prolog code is written by human, and what's your expectation on its end goal?
Yeah, so we use Prolog in this case because it fit. It doesn't necessarily follow that Prolog would be our ultimate choice for the ontological reasoner. As you, obviously from your question, you're reasonably familiar with this, the ontological reasoners are fairly limited. So in this particular case, Prolog worked very nicely for us. But somewhere down the line, there's going to have to be some work that improves on the ontology reasoners. And at that point, we can rely on them. And I think I missed your second question, did I?
What percentage of the Prolog code are written by human, and what's your expectation on its end state?
Yes. In this particular case, it's portions of each. So there's some that have come into the system directly, and there's some that a human has constructed. Ultimately, we're going to end up with an ontological structure that defines the whole thing, and as we extend it, we'll be looking for additional extracts of ontology to fit into it. I couldn't give you a percentage right now. That I couldn't do it off the top of my head, but we can have a chat afterwards if you want. I think there was a question here. No microphone for the lady? Oh, no. Just shout. I've got you.
So just want to bounce off the question about errors propagating through the digital twin. So I guess one way that I see it is if there's transparency in the kind of data that is used, which again to me comes back to good quality open source data. So are there any efforts at RBC that can curate, that can support the curation of open source good quality data?
Yeah, there are everywhere. Yes, there's a lot of that going on. I think one of the things that's going to help us, though, is if we've done a really good job of the ontology for the digital twin, because that's going to reject a lot of things that really are fundamentally erroneous. My example here, fields are associated with a farm, right? The fields are not necessarily contiguous, but it's not particularly hard to check downstream. And if that link isn't there, then you've definitely got a problem. You can't have an unassociated field in the digital twin because the schema simply won't allow that. All right, I think I'm ready. Thank you.